Ever wondered why your glasses sometimes reveal a rainbow? Let's uncover how tiny prisms inside lenses split light into color. Light travels in straight paths until it meets a boundary. When white light hits glass, its speed changes and the beam bends. This bending is called refraction and depends on wavelength. A prism is a triangular piece of transparent material that magnifies this effect. The incident ray enters at one face and exits through another after two refractions. Each color component slows differently inside the glass, so they separate in space. The result is a spectrum ranging from violet to red spread across the exit angle. The separation demonstrates that white light is actually a mix of many colors. In everyday glasses, prisms are used to correct vision by redirecting light into the eye. They also serve as educational tools for visualizing wave behavior in optics labs. By observing the spectrum, students can link theory with tangible evidence. Thus, prisms reveal both the physics of refraction and the composite nature of light. Pause 0.8. When a beam of light hits the surface between two media, its path bends. The amount of bending depends on how fast light travels in each medium. We quantify this speed difference using the refractive index, n. Snell's law states that n1 times the sine of the incidence angle equals n2 times the sine of the refraction angle. Mathematically, n1 sin theta 1 equals n2 sin theta 2. If light moves from air into glass, n2 is larger than n1, so theta 2 becomes smaller. This reduction in angle causes the ray to bend toward the normal line. For each wavelength, the refractive index changes slightly. Blue light has a higher n than red light. Thus, when white light passes through a prism, each color bends by a different amount. The cumulative effect spreads the colors into a spectrum that we can see. By measuring theta 1 and theta 2 for a known material, we can calculate its refractive index. This fundamental relationship underlies many optical devices, from glasses to cameras. Pause 0.8. Light enters a prism and splits into colors. This happens because glass bends light differently at each wavelength. The refractive index n is higher for blue light than for red. A plot of n versus wavelength shows a gentle decline across the visible spectrum. When the beam hits the prism, each color follows a slightly different path. Blue rays bend more sharply. Red rays travel almost straight through. The angle between the emerging beams is called the dispersion angle. Dispersion is why we see rainbows after rain and in glasses. In everyday lenses, small amounts of dispersion can cause chromatic aberration. Optical designers counter this by using achromatic doublets or special glass mixes. A crown glass example shows n decreasing from about 1.55 at 400 nm to 1.51 at 700 nm. This small change is enough to separate colors by a few degrees, visible as a faint spectrum on the other side of the prism. Pause 0.8. A prism's apex angle is the key to how light bends. When sunlight enters, each color refracts at a slightly different rate. Red light travels slower through glass than blue, causing distinct paths. The deviation angle depends on both the apex angle and the color's index of refraction. A larger apex angle pushes all colors further from their original direction. Conversely, a narrow apex keeps the spectrum closer together. In everyday glasses, designers adjust the prism to balance clarity and color separation. This adjustment ensures that vision remains sharp while minimizing unwanted rainbow effects. By visualizing the 3D model, students see how each ray bends at specific angles. The red ray exits with a smaller deviation than blue, illustrating dispersion. Mathematically, the relationship follows Snell's law and the Prism equation. Understanding this mechanism helps explain why glasses can correct vision without color distortion. Pause 0.8. When a beam of white light enters a tiny prism built into a prescription lens, it bends. The prism's angled surfaces refract the light at different angles depending on wavelength. Shorter wavelengths, like blue and violet, are bent more than longer ones such as red. This separation creates a miniature spectrum that can appear as faint color fringes on the eye's retina. In everyday glasses, these prisms are euros, often less than a millimeter across euros, to avoid distortion. The prism's orientation is carefully chosen so that the color shift moves away from the line of sight. Thus, while correcting vision, the wearer may notice subtle rainbow euros like halos around bright lights. These halos are harmless. They result from normal refraction and do not indicate a defect in the lens. Optical designers use precise calculations to balance vision correction with minimal chromatic dispersion. By adjusting prism power, manufacturers can reduce visible color fringes while maintaining prescription accuracy. Pause 0.8. Place the prism on a stable surface in front of the flashlight. Turn on the flashlight so that its beam hits the prism at an angle near 30 degrees. The light enters the prism and slows down because glass has a higher refractive index than air. As it exits, each wavelength bends by a different amount. Shorter blue light bends more than longer red light. This bending is called dispersion, and it separates the white beam into its spectral components. Observe the resulting rainbow projected onto the white wall behind the prism. Notice that the colors appear in order: violet, indigo, blue, green, yellow, orange, red. The separation occurs because each color travels at a slightly different speed inside the glass. By adjusting the angle of incidence, you can change how spread out the spectrum becomes. This simple setup demonstrates the same principle that makes everyday sunglasses and camera lenses work. Pause 0.8. Prisms are simple glass wedges that split white light into a rainbow of colors. In photography, a prism filter can correct color casts by aligning the spectrum with the sensor. The filter works by dispersing light before it reaches the camera, ensuring accurate hues. Spectrometers use prisms to separate wavelengths so that each can be measured individually. A handheld device shows a spectrum on a screen, letting technicians calibrate instruments quickly. In stage lighting, prisms create dramatic color effects by projecting split light onto the audience. Artists can manipulate the intensity of each color band to evoke specific moods or themes. Because prisms are passive, they add no power consumption and require minimal maintenance. Their compact size allows integration into portable gear, making them ideal for ONA Euros Thea Euros Go setups. Thus, everyday glasses can harness prism technology to enhance color fidelity across many fields. Pause 0.8. We explored light as an electromagnetic wave, applied Snell's law to show refraction, examined dispersion through wavelength Euros dependent refractive indices, linked prism geometry to color deviation, and finally saw how everyday glasses use tiny prisms for both vision correction and spectral separation.